in remote sensing and GIS application. He has a vast experience in almost all the applicable domains of remote sensing and carried out project work in the area of optical remote sensing, hyperspectral remote sensing, photogrammetry for multiple domains of application. He has vast experience in the application of remote synthetic aperture radar, microwave remote sensing. He has worked extensively for digital elevation models, persistence interferometry, SAR polarimetry, and many towards environmental monitoring and solving common sustainable issues. He has published several papers covering the landslide, earthquake building subsidence, dam subsidence, and crystal deformation. He has been associated with several space agencies such as European Space Agency, Japan Aerospace Exploration Agency, and DLR to carry out the state-of-art in-field of application development using SAR data. He is also involved in imparting training to faculty, scientists, and students all over the country and the world in the field of SAR remote sensing for many years. He is also part of the SARS Pros team, India. So again, I welcome you, sir, and request you to give us the insights on the topic of interferometry for land deformations. Welcome, sir.
Thank you very much, and good afternoon, everyone. I really, thankful for providing me this opportunity to showcase the work which I've been doing in the last few years, and I think the participant will benefit out of it, and in future we look forward to assist you in case if there is any requirement. Whether it is in the form of technical consultancy or either academic collaboration kind of thing. So today I'll be speaking on this subject. Let me just try to share my presentation, and I think yes. Can you please confirm if you can see my screen?
Yes, we can.
Okay.
Yes.
So today we will be talking about the interferometry and its application in the land deformation monitoring, and I will try to cover some of the basic principle for the newcomers in the field, and some advanced analysis where we will be talking about some of the case studies in land deformation in the different field. So first of all, this is very brief outline what this presentation has. Introduction to the SAR and its merit and demerit. SAR interferometry, some terminology we will be talking about in-SAR, in-SAR processing steps and phase unwrapping. And then we will talk about the multi-temporal SAR, that is time series data processing, atmospheric phase screen, and persistent scatterer interferometry. I've selected some of the example which we try to cover in this 45-minute session, that building subsidence, dam stability monitoring, landslide monitoring, detection, etc., and something related to the mine subsidence, and some in the last I'll try to show you the software which the software I've been using to process the SAR data and carry out the different work in this domain. So first of all, we need to understand how this INSAR work. This is basically a interferometry terminology itself is when we are talking about more than one image, when we are talking about the two images which is acquired using more or less the same, the sensor parameter and over the same, the piece of earth, and we are trying to be on the same location when we are trying to take this image. So when we have the two different images which is having almost identical the parameter of image acquisition, coverage, etc., those to the image we called as interferometric pair. And you can see in here in this visualization that this platform is doing a repeat pass, coming after some time on the same location and collecting another image, and it captures the two things, the amplitude as well as the phase information of the surface. So you can see more correctly here now. This is how the INSAR data being collected. And now the more focus would be on the the persistent scatterer in this talk. So I have just clubbed this one slide over here before we further go into INSAR and DINSAR and the SAR merit demerits. That permanent scatterer is like basically the building or any object, man-made or natural, which is permanently available in the image series. So for example, you acquire two images and there are certain object which is available in both the image. That is very much the easy case. But when we talk about the time series which is covering a time span of 5 year or 6 year or maybe more, depending on the type of data we are using, then identifying those permanent structure over a period of 5 to 6 years become very complicated, and it is very important to identify those permanent scatterer in order to estimate the displacement or the velocity or the or detect the land deformation on that area. So the permanent here you can see in this picture that permanent scatterer is the building, etc. And there are certain other things which keep coming and going. For example, the vegetation. For example, if there is some construction activities happening in one area, there was nothing in previous images, but now there is some building has appeared. So those building cannot be called as permanent scatterer. The permanent scatterer is basically the one which is available throughout the image series. So in the next, you can see there, this is not very important. Let's move on further. Yeah, here you can see that these are in the red is basically the permanent structures which is available throughout the time series, and those are our initial point of reference where we will be trying to estimate the deformation for land deformation. Land development. You can say the surface movement or anything, depending on the type of work we are doing. So we talk about the SAR limitation. As we aware, like mostly, we acquire our SAR data in a, you can say, using the synthetic aperture radar, and it always look in the side. It does not look as we see the optical and hyperspectral remote sensing. The technology, the terminology which we use is nadir looking or the side looking. So SAR is basically side looking, so it has its own limitation in capturing the what we call here is apparent view and actual view. So we have to be very cautious about it, that how we are capturing the image and how we do the further image interpretation. This is again, we will be talking about the limitation, like all signal are mapped into reference plane. This lead to the foreshortening and layover. So these are 2-3 things which when you will be starting the SAR data processing, it always come what is the foreshortening, what is the layover, what is the shadowing effect. So in these 2-3 slides, we are trying to make sure that you understand how it works and what is the meaning of these 2-3 things, which is very important in SAR. So the foreshortening is basically, you can see that if there is a ground elevation is there is, for example, a very layman example I used to give is if you are sitting somewhere and there is a hill or hillock somewhere you are looking at, then you cannot see the other part of the hill, which is just opposite to your the position. So those kind of things, like when we actually make an image, they play a very important role, and there's some of the area which fall into the foreshortening, and we have to do some sort of adjustment in the SAR pre-processing for that. Same thing is the layover, just opposite to that, the layover also happen in the same direction. Is it okay? Or either I'm too fast, sir.
No, this is fine. If you can switch on your video, it'll be good.
Okay, I'll see when I'll come to the other slides, sir. So the shadowing effect is also, more or less the same thing, which is very important when we are dealing with the SAR data processing. So all these things come into the are pre-processing, and we hardly deal in direct form in SAR data processing chain. So now we quickly run through some of the the advantage of the optical remote, the SAR remote sensing over the optical remote sensing. The SAR provide all weather capabilities. It is very sensitive. I mean, not very sensitive to the cloud and light rain, so we can see through. And it provide the day and night, monitoring, as it is not dependent on any natural source of illumination, and it has very limited effect of atmospheric constituent. And if you are using multitemporal SAR images, we can also minimize that atmospheric artifacts, and it is very sensitive to the dielectric properties. SAR in the very beginning, SAR was basically used for soil moisture estimation purpose, because it is very much sensitive. If anything, I mean, the water content change in the soil, it is very sensitive and provide a very accurate information about the moisture present in the the soil. So based on that, there are lots of application has been built in the field of agriculture, and estimation of the biomass is also somehow being done using the SAR technique. SN, it is very sensitive to the surface roughness. SAR is very sensitive. Even we can detect the you can say the ripple in the ocean or any water body, which is basically being caused by a wind. And the most important application which we will be talking onwards is the interferometry, because SAR estimate the measurement, an accurate measurement of the distance. I mean, SAR is very useful and very accurate in measuring the distance. And as I before we were talking about this it is very sensitive to the man-made objects such as buildings, etc. So they provide the better backscatter, better reflectance, you can say, in terms of the optical remote sensing, and those man-made object can be seen very well in SAR image. And we can also use the different polarimetric or different polarimetric data for in different polarization to really look into the what is the type of structure it is. I mean, if it is heterogeneous, homogeneous target, we can also do that kind of identification using the polarimetric SAR. And in last, it up to certain level, higher wavelength is can penetrate in a ideal condition up to certain level in the ground, and then they can also provide some subsurface information. Okay, this is an example. Very well, you can see this slide most of the time when you are saying SAR data related presentation, that what is the merit and demerit. This picture clearly tell. One, we have the ERS, that is a SAR image on the left hand side, and the right hand side we have optical image. So they all are taken almost at the same time, roughly 1.5 2 hour difference. And this is a cloudy condition, so SAR can penetrate and can provide a very accurate information of the Earth surface in comparison to the Landsat data or optical data. As we have been talking about lots of merit of the SAR data, but there is some difficulties as well in the processing and in understanding the the SAR data. First of all, the visual interpretation is very difficult. There lots of speckle come into the picture. I mean, they produce not higher backscatter value, which also sometimes does not make it also create lots of noise, you can say, in more specifically and more in layman language, which is not good for further interpretation and identification of the object in the image. And topographic effect, yes, as we were touching upon, like layover, shadowing, it is very sensitive to the topography because of the side looking phenomena over here. And effect of the surface roughness is also produce lots of if the surface roughness is just changed, nothing else, it also produce lots of implication in the SAR image. So these are some of the merits and demerits of the SAR data. And now we talk about some of the example in the land deformation. So I have 3-4 different studies where we will be, trying to show you what we can do with the SAR data time series analysis to produce the land deformation map, or you can say to estimate the surface velocity in any given case, whether it is a barren land, petroleum exploration activity happening underground or somewhere in the in city, and we see some deformation. That deformation can be detected using SAR data. Then another example is for dam or any other infrastructure project or any other big building where we want to see if there is any deformation or if there is any instability in the building, that can also be detected using SAR data. We will also talk about the landslide detection and monitoring. And I think I do have one example of a subsidence in a mining area. So first of all, we start with this urban subsidence example. This is one of the work which I have done using the TerraSAR X data. Total number of images is 64, and it covers a time period of around starting from 2011 and goes up to 2013, and so roughly you can say slightly over 2 years. And they are 68 images, very high resolution image. And this is one of the very basic flowchart of SAR data processing in any of the given software. You can use any software. This is more or less the same. First of all, you automatically detect the master, do the subsetting depending on the data you are using and the area you want to process, then performing the co-registration. Co-registration is just to make sure that all the images are adjusted in a rubber seating mode so that we can do the further interferometric processing. And the TOPS processing is not included in here, but if you are processing the Sentinel data, then the TOPS processing would also come into the picture. Then generation of the amplitude stability index is a very generic processing steps in PSINSAR data processing, and then selection of the GCP, etc., and conversion of the external DEM. We will also use external DEM in any of PSINSAR processing. And there are after this there are two different you can say the processing chain. One is for APS, that is atmospheric phase screen selects estimation and removal, and second one is for estimation of the velocity. Once we do this velocity estimation, we can probably generate output in terms of, like, we can export them into Geotab, KML, and Excel for further analysis. So here this is amplitude stability, reflectivity map of that study area. You can see the river Yamuna in the center of the data, and you can also see the airport over here. This is Delhi NCR, the part of Noida and part of Delhi. Now this is a vertical cumulative displacement map which we have generated using time series, these 68 images. And you can see this part, which is in the red or yellow, is showing some amount of deformation, while most of the part in the left hand side is stable, but still there is some certain patch which is we further investigated in order to estimate what is the magnitude of the subsidence and what is the probable cause behind it, and what is the behavior of the subsidence over the period of time. So this subsidence was linked with groundwater depletion. So here you can see the groundwater data is also being plotted over this area. So this was a bore well in Gazipur crossing area. If you are familiar with the name of this area, the groundwater level has been dropping over the period of like 2.5 years. You can see starting from 2014, it goes up to 2012 to 2014. It has depleted around 4 meter in this particular area. And when we look at the grounds, subsidence, and this is the trend which we are, estimated using our data set. So you can see every year after the monsoon, you can say after July, you see some change in the pattern, but overall, this area was showing some amount of subsidence. Roughly, you can look at here the cumulative displacement around 32 millimeter, and the velocity, yearly velocity, was 1.5 centimeter or 15 millimeter per year. We also did some sort of interpolation and generated a map of the the borewell data, and these are some of the area which we identified showing the groundwater depletion. which is also being reflected in the resampled velocity of the ground deformation estimated through SARS data. And this item was published long back. Again, now we come to the dam deformation. This is one of the example in Himachal Pradesh where this dam we have taken, and we use the sentinel images. The timeline starts from 2016 Jan and it goes up to 2022. And number of images for this study we have used is 166 of sentinel. So here you can see that the base spatial and you can say the normal baseline or the temporal baseline distribution of those images. And this is the final outcome which we have generated. I think this is much better. So here in the center of this dam, there is some amount of deformation. These are some of the noise point. We can eliminate them. But here I just wanted to show you the overall, output without filtering, and just to, give you a fair idea how we estimate it. And there is one more. Yeah, no, not here. So this is the one of the interface of the software. As of now, this you can see the highlighted is deformation trend. So this is the deformation trend, and look at the scale bar. The minimum and maximum is around 8 millimeter per year. So here in the center, we are working on it. We are, also comparing it with some other data set in order to estimate what is the cause behind it, and how this one part of the dam is showing some amount of subsidence. This is one example of landslide. This is somewhere in the northeast India. We have used some 73 images of sentinel, and you can see that their normal baseline distribution versus the temporal baseline distribution. And here you can see this is a output generated and finally exported to the Google Earth. So these are some of the area where we can see some amount of landslide, which is also being confirmed on the ground. And I think this year in the month of July, there was this big event happened in the Tupul. You can look for this in internet. There was news about it, and I think there was some casualty was also associated with this event. So this technique can estimate the amount of deformation taken place, or it can also detect the landslide. And sometime even, I mean, in mining area, we have done some work where we can even predict the subsidence, because in mining area the most of the parameter is controlled in comparison to here in this. And you can see the timeline. We have selected this point over here and plotted the timeline. So this is how over the period of 2.5 years this the particular point was behaving. The overall deformation on this point, the cumulative displacement was roughly 16 centimeter, and the velocity was around 6 centimeter per year. The total number of images which we used, as I already said, that 73. Now this is another example of urban subsidence. We can leave this. Yeah, this is very important actually. So we start from here. So we used 62 images of sentinel. You can see the parameter of the sentinel, very well known fact, and spatial and temporal baseline distribution of the data. And this is very standard processing flowchart as we have used for processing. This is TOPS processing is also included, as this was a sentinel data which need TOPS processing as well. And this is a resampled output map, which is giving you some idea that there is certain area where there's some amount of deformation is taking place. And we see this one is very important. So this particular point which we have identified, it is also confirmed at the ground that there was some amount of displacement happen in this area. Here what we have seen or observed is this. Look at this data set every year around April. It shows some amount of rapid change that is linked with the groundwater situation in this township. And they have confirmed it on the ground that there are certain building which show the cracks in the pre-monsoon time. I mean, when the groundwater goes exploited more and the level goes below, and then some amount of subsidence can be seen on the surface and these buildings. So probably some crack or something like that, some evidence, that kind of evidence. Most of the area is stable, but there is certain highlighted area like which we have identified over here is showing the subsidence pre-monsoon. Now we come to the next example. This is a mining site where we could identify the displacement, vertical displacement, and you can see that is also being validated on the surface. And when we plotted the time series for these three different zones, this was the behavior. Like there was a spot 1, 2, 3. So there some consistency. The trend is different, but all of them, all three are showing subsidence over a period of time. Now this you can see these point data as well on the same site. Here this was the area which was showing the subsidence and which can be detected using time series SAR data. Now I would like to show you the software. I think that is the best part to really see how it works in SAR data processing. So this is one of the example I have loaded. Let me just go back to another load. I'm going to load that dam data which I just shown you. Yeah. So this is the total number of images 166, Sentinel 1, and here you see how the software look like. This is 4 different button. You can call them. This is for data importing, doing the subsetting. Yes, sir.
You have
yes,
to
sir.
share that window for software. Okay, you can't.
Oh, okay. Sorry. Stop sharing, then share. Share. And what to share? Windows. How to share all?
Screen.
Yeah. Can you see
You
it?
can see. Yes.
Okay. So yeah, so I'm just trying to show you some of the tests we did on a site here. For example, this data is already processed, so I load my reference point based on some threshold, some parameter. For example, I use this threshold and this parameter amplitude stability index, and we go to the scatter plot. So we plot in the line and sample and select the color as deformation trend, and this is the reflectivity map. So here you can see that this is the dam area.
We are not able to see some black screen is there. Some gray screen.
Sir, how to share the complete window?
Yeah, go to this share button, then entire screen option is there or screen.
Yeah, it is not coming here. Can you see it now, sir?
Yes.
Okay. This was the first one, sir. Okay, so here I have just trying to plot. This is the reflectivity map, and we are plotting these points and their deformation trend. So here you can see some point has appeared in the water body as well. So I'll try to put a condition that reflectivity map value more than 1. So now we see I also limit the maximum and minimum plotting range, and also decrease the size of the point which we are plotting. And so now we finally zoom in this area. You can see that there is certain point which is showing some amount of subsidence. We can do further analysis, and yeah, one thing which is very important in case if you want to see only those points which is temporally coherent and which is permanently available, so we can put another threshold of temporal coherence 0.5 or anything. The total number of points before this threshold was 10,720. Now it is only 17. So if you plot them again, you will see the point which is highly stable throughout the time series, like the dam. Now the picture is more clear. If you go here and zoom in, you can see that these are the points which is thoroughly available. And in the entire time series they were available, and they are showing some amount of deformation in the center of this. If you can increase the size, and now you can plot it. So it is clearly seen that this area in the center is showing some amount of deformation. To make sure that you further do some detailed analysis, I take you to the another processing window. It will not take much time. Data is already processed. We are only doing the visualization and discussion about it. So, I mean, this is very important to first of all identify the very stable persistent scatterer, which is basically the first starting point of our time series analysis. If we do not get sufficient the persistent scatterer, then we will not be able to do the time series analysis. Then there has to be some customization in the processing chain, and I just change this one, force reloading and geocoding. So here we can see all the parameters starting from coherence, height, deformation trend up to the cumulative displacement, depending on the the parameter applicable. So we can remove the background and I load only the deformation. I change the limit for plotting, plus minus 9 we keep, and now you can see clearly that this area is showing some amount of subsidence. If you want to see the time series, we can also plot the time series here, and you will see the trend of the deformation, or how it behave over the period of time. So you can see that it go up and down. There is some trend. We are trying to correlate with this with the availability of the water height in the dam, and but still you can see the model, that blue line, so that this point is showing some amount of deformation over a period of 5 to 6 years, whatever the data we have starting from 2016 and goes up to up to 2022. So this is one of the work, and we can also do some analysis based on changing the background. So here you can change the background to Google Earth, and if you want to see the coherence of these points, yes, these are highly coherent point over here, and you can also see the height of those points. And one thing which is very important I would like to show you is this. Yeah. So in the black line we have the height profile of this point, whether the point location is shown in the red, and the line of sight. Please note that all the measurement in INSAR what we do is in the line of sight. That is the image acquisition, how we look at the surface, using some the incidence angle, the center of the I think it is 23 degree for sentinel, but in the near range and far range it change. So all our measurement is in the line of sight. When we are actually doing the the comparison with the GPS or any other the data, or you can say we are checking with the field data, we have to consider that our estimation is in the line of sight, which need to be converted into vertical or either east west, whatever way you want to compare it. So our estimation is in the line of sight, and you can also see the cumulative displacement of these points. So we change the ligands again to plus minus 6 only. Yeah, so over the period of time you can see here the cumulative displacement is also very high for these points. But these big infrastructure project has lots of strength. They can bear some amount of force, or you can say they are kind of resist some amount of the displacement and come back to the natural you can say the position even after when the force is removed. For example, if the water is filled, it can absorb that, it can produce some resistance and displace maybe 1 or 2 millimeter. Once that water is emptied, then it again come back to the normal. So this is this is all about the cumulative displacement, deformation monitoring, or you can say the land deformation using PS in SAR. Maybe we can extend further if there is any question to the any specific area. I would like to talk about that in instead of showing whatever I've been showing. So if you have some specific question you want to ask, please let us know. We try to focus on that and provide you some more possible insight into it.
So did you have some analysis when the reservoir is empty or less water?
Yes, sir. We have collected that data. I can see it here. I just plotted a couple of days back. Water level data. Yes. So we have collected the data. This data is available in the public domain. And when we plotted it, something like that has come. The water level keep changing over the period of time. 2019 onwards, we have this data up to 23. So every year, pre and post monsoon, you can see it filled, and then it empty again. You can see the level here in the meter. It goes up to 1400, or you can say 1380, and it come to 13 sometime pre-monsoon. So we are trying to link this deformation pattern with this data. I have done some plotting as well, and up to certain level it is matching with this. Yes, it is. And for example, as I already we were saying that this slide, groundwater depletion, the same case happen here. You can see that every year in the month of pre-monsoon, the you can say that the trend reverse. It does not continue to subside in monsoon or after the monsoon. But as soon as the winter comes, it start again, subsiding and keep subsiding up to the monsoon comes. And here this is very rough map though, but still it is matching with the what we have identified, that this was the area where the groundwater depletion is happening in meters, and this is showing the subsidence. We do not have the data point over here, otherwise it could have been extended in that direction as well. Here we could not identify a very good PS point, but still this area is having a different trend, and which is matching with the groundwater condition in this area.
So there's a couple of questions in chat. I'll read for you. Okay.
Yes,
So
sir.
do we need the ground data for the measurements? If yes, what type of data we need?
Sir, in the true sense, if we want to see the subsidence, for example, the amount of subsidence is very huge in Josimat. We do not need a DGPS data for that. But in case if the slow crustal deformation is happening, we always suggest to have like a DGPS data, or in mining area, in a very confined area like a mining, we also collect the labeling data. So these are the three different form of the data. One is the labeling, geodetic technique. We can use that for that, and GPS for a larger area. And when the amount of subsidence is very high, then you simply the field visit can tell you the story, if the subsidence is happening or not.
Yeah. And another question is very interesting. Yeah, of course you can do. So it's asking, can we do a similar exercise for glacier velocity in the Himalaya region? Of course, yes, using SAR approach. And that questions come to you again. So is the SAR approach license software, maybe you want to ask, available freely or something? I don't know. The question is not completed. Okay.
Okay.
Yeah, it is licensed software. Okay.
So there are two things. One is whether we can use it in the glacier, or whether the software is available for the research purpose. Yes, both are yes, but in using this technique in as we have been talking at every 5 minutes about the persistent scatter, about talking about the reference point, the point which we identify as a reference. If you can identify the reference point in a glaciated, in an area of your study, then definitely we can run the time series analysis. But I think in a true glacier, when the glacier keep moving every year, every day in some case, so we will not be able to do the time series analysis on those area where the the Earth surface is moving. because it produces lots of decorrelation, and we will not be able to identify our, the persistent scatter or point or reference point. As far as the software license is concerned, yes, for academic or for research purpose, we provide trial version as well as some hand holding initially to help you to do some sort of case studies, at least one case study end to end, so that if you want to replicate, you can do yourself for the another case study or another study area.
Oh, so one more question. Okay. I
Yes,
think
sir.
it is a deflection, not deformation. The displacement obtained after the dam deformation, I want to correct it. It is deflection, not deformation. Analysis is vertical displacement or horizontal?
We just covered this, the item. And first of all, I mean, for a civil engineering purpose or for the profession from a different field or actual civil engineering field, you can call it whatever. But in my view, I'm looking it from the satellite, and we are doing the estimation in line of sight. So if anything is changing in the line of sight, we say it. We have the two different terminology for that. One is upliftment, one is subsidence. If it is coming towards the satellite, that is upliftment, which can be a which could be anything could be the region behind it why it is coming up. And second one, which we say subsidence, it is basically going away from the satellite. So whatever the region is, whatever terminology you call it, but what we say is upliftment or the subsidence. If it is going up, I mean coming up towards the satellite, then upliftment; going away is subsidence. We measure all these things in the line of sight of this satellite. So as this is the example, you can plot it again here, that this is the line of sight. You can also see what is the local slope over here, what is the incidence angle of the this particular point. In case
Okay.
we do have a module, sir, where we can, there is certain requirement sometime comes up that way, that they want to estimate the line of sight velocity, vertical velocity, or east-west velocity. So if you want to convert them, there is a possibility we can convert them into any customized direction for further validation verification purpose.
So, okay, there are several questions. I will give quick, short answer, maybe not bigger one. So otherwise we will be lacking
Okay, no
time.
problem, sir. No problem. I thought that
Uh,
is the only question left.
yeah, I think the questions from Ajay Kumar is slightly different. It is not from interferometry perspective. Experimentally, how we measure the behavior of reflected echo from the target at the detector. Maybe it's something GPR related questions, not interferometry one. Maybe you can have the separate discussion directly with the.
Yes,
Yeah, I
very
think
good.
it's from Jammu. Okay. So then another is this software present in MATLAB. Yes, this is in MATLAB. Okay. And another
But it
one.
does not require MATLAB license to run.
Uh, So another one is that it's asking that any coding knowledge is required
No.
performing these data analysis. No. Okay, this is like user friendly. Okay, you
Yeah.
have to just do the thing. Okay. The next question is from Somdeep Kundu. So he's asking how we are getting points on water, and is there any way relationship between the wavelength of SAR, microwave, and interferometry? Is yes, and then when which band is better? Is asking something like a basic question. Okay.
Yeah. Well, in water, this is just a noise. When you see in
No,
this
it
picture,
is.
we put a threshold and those point has been eliminated. There is no point in the water body now.
Yeah, and of course there is a relation between wavelength and
Yeah.
interferometry performances. Okay, so if
Yeah,
you
Doctor, you can explain it, sir.
so it's something like depends on that. Okay, half of the wavelength
How about the
can be the
wavelength?
maximum adjustment displacement can be measured by the
Yes.
interferometry. Okay.
Yeah. How about that?
Uh, and that downstream side. Yeah, that was very interesting questions again from Somdeep. It's asking that ISRO is going to launch NISARs mission or satellite soon. So what are some benefits of having dual band SAR system for these kind of interferometric deformation studies?
Well, honestly speaking, band is one thing. I mean, there is certain limitation and merits and demerits associated with each band. But interferometry, what is more important is the number of the data points. For example, how many data you collect, what is the repeat time for a satellite. Let's say we talk about the Sentinel, so every 6 to 10, 12 days they produce the image. So more the image, more accurate or more robust information you can generate. As far as the wavelength is, I mean the band is considered. I don't see anyone built a kind of combined interferometric processing for both of the data. For example, even now we have the dual polarization data. We process each polarization separately. So if the NISA data comes in, dual frequency, yeah, definitely we can process them separately. Let's say, I mean, more we can say when we actually have the data. But in interferometric, from the interferometric point of view, it is more important to have more number of images in compare. I mean, instead of having a multiple band.
Okay, so that last question is that can we implement S-bus in small baseline? Okay, also using this software, or can this PSNs are helpful for sonograph measurements?
These are the different graph which we can implement, whether it is the MST, minimum spanning tree, full graph, small time baseline, and Delune. Depending on the type of the data we have today, which we have covered, is very easy to process. We get the target easily. We get the persistent scatter easily. In case if we are processing some complex strain, definitely we can try the different method. And those things are implemented in the software as well.
That one more question is there from Nitin Hunti. He's asking like some changes, okay, toward the downstream. You can see several points are there. So these changes are like some displacement or erosion. What kind of these things happening?
It is definitely a displacement, sir. If erosion happen, the decorrelation happen, then we will not be able to get these points. So these are certain, the objects which is showing some amount of displacement.
Okay, so these are the questions. Can these patients are helpful for sonograph measurement? He's asking again this question. Okay, I don't know. It is sono itself very changeable environment. Okay, so getting any correlations and permanent scattered in so much very tough situations. What is your comment, Kapil, on this?
Sir, no comment. I'll just show you one picture. I think I already shown you the one a few days back. Where is that?
So sono depth is possible using PSINSAR?
No, I mean we can really not say, but in case of all our game is on the persistent scatterer. So what we were seeing is that we are trying to estimate if they're moving or not moving, and if they are moving, how much they are moving. So estimation of the depth is somewhat not directly linked with interferometry, but yes, there is some work, using L band and different wavelength or maybe UAV based SAR. They are doing something, but depth basically they are talking about the snowfall and the amount of accumulation, sir, something like that.
Sono depth, sono depth, sono depth.
For that, sir, people use GPR only. I mean, as making that measurement accurately, GPR is the best solution.
Okay. Okay. So no more questions. If you want to explain something.
Well, this is it, sir. Again, first of all, thank you very much for inviting me over here and providing me this opportunity to interact with the lots of people in this domain. And we again our offer is here that in case if anyone is interested, he can reach you and you can direct him to me. We will provide a trial version. They can try the software themselves and maybe probably can run one or two pilot project, and and ensure that they learn the land deformation using SAR interferometry.
Okay, so thank you, Kapil. Varsa ma'am, conclude the session, please.
Yes, sir. Thank you so much, Kapil sir. First of all, for accepting our invitation in a very short time. I take this opportunity to thank Kapil sir for he has given us insights about the said topic in a very concise manner, right from what are the advantages of SAR, especially in the sectors like agriculture, water, and he have given us the examples with respect to the comparison of SAR data and optical data, what we actually see. He has shown us with the comparison. Then he has also given us insights on various projects and results that he was working on with respect to groundwater depletion, dam deformation, mining areas, and also he has answered various questions that the users have posed. Of course, I am very novice to this chapter, but little insights I could get about SAR. And of course, we would like to have more details with respect to practical orientation. From what I understand, Kapil sir, I think so, the software that was used was MATLAB. I had a one personal question whether is it feasible to do in QGIS, which are free softwares, or Python programming, whether we can work on SAR images. I really thank him for these all things. Actually, my net is little not supporting, so I couldn't post the question in the chat box. So sorry for that. And I really thank everybody. I thank Gulab sir. He has coordinated almost everything about this webinar, and also all the participants for actively participating and posing questions so that we could get maximum from this webinar. So thank you all.
Thank you, ma'am.
Thank you.
Thank you very much. And if you, I can answer your question very quickly. QGIS does not have the SAR SAR interferometric processing capabilities, but this is a commercial software. But we are very generous to support the academic activities. In case if there is any research, anyone wanted to use the software, please feel free to reach us, and we will definitely help you out.
Okay, sir. Thank you so much, sir.
Thank you.
Yeah, thank you, Gulab sir.
Thank you all, everyone, and thank you, Dr. Kapil, for accepting our invitations. And I appreciate your supports, your talk, and very fruitful discussions with the participants. And you have given very good answers to all the queries, doubts of the participants. So I thank you very much and appreciate your.
Sir, can we have one picture? Can the cameras be kept on for everybody?
Yes.
Please. Your coordinators request you to, I don't know how much my screen and my network will support.
What can you do? Yeah.
View, complete view.
I think you have to allow everyone to open the camera.
Yes, that centrally coordinated I did. Hello, sir.
Oh, please.
Can everyone try to make that camera?
Yeah, please switch on the camera, all of you all.
You can make this gallery view and try to take picture without camera. Anyway, take this one.
Yes, sir, that I have already allowing.
Since many of you didn't open the camera, so we We are taking with us only.
Yes, sir. This I have clicked.
Okay, one more setting. You don't see your meeting options. The option. Since everyone open, absolutely A is open. यहाँ पे से allow camera ऐसे allow camera. Okay. Allow mic having permission. I'm giving permission to open the camera. So it was my fault.
Yes, now they can open.
Yes, now people are joining.
Please try to switch on your camera. Sorry. So many known face, many unknown face. We're seeing first time. I hope everyone has enjoyed this lecture. So I can see the smile on their face. Shruti, see Lakshmi, didn't open your camera. Bala. I think enough. Okay, just now. Picture. Okay, thank you. Thank you very much.
Thank you, sir.